Okay, so let's start with what is linear regression. And excuse my handwriting, I know it's bad, but the reason it's bad is, and I misspelled, okay. The reason it's bad is because I'm trying to write really fast. So imagine you are running a lemonade stand. I'm gonna draw a lemon for you here so that it's easier to visualize. Okay, okay, you have this lemon and you are running a lemonade stand. Okay, you have this stand right here. Lemonade. Okay, you notice that on hotter days you sell more lemonade and on cooler days you sell less lemonade. So wouldn't it be great if you had a very simple way to predict how many cups you'll be selling based on the temperature of that day? Well, that's exactly what linear regression helps us to do. So linear regression is a way to find patterns in data by drawing a straight line that best represents the relationship between an input like temperature. So I have temp here, which is my temperature, and then my output, so this is the input, and then my output, which is lemonade sales. Lemonade sales. Okay, so in simple term, I am saying when it's 10, when it's 20, all the way to when it's 80. When it's 10, I am selling 0, or let's say I am selling 0 lemonade. And then when it's 20 degrees Celsius, let's say I sold 2 lemonades that day. But when it's 80, then this isn't a large enough scale, so I'm going to go bigger. I sold not 1, 2, 3, 4, 5, 6. Wow, isn't that amazing? Okay. So I sold 6 lemonades. So by drawing what we call a best fit line, which is basically a straight line that sort of best represents the relationship between an input, the temperature, and output. And this is my attempt of drawing a straight line. It describes that relationship, and you can use that line to make predictions for future. So I know if the line looks like this, a certain day when I know it's going to be 70, then I can go here and predict how many lemonades I might sell and how much dollars I will earn. I forgot to mention $1 equals to 1 lemonade. Okay, does that help? Okay, so we drew the straight line, and in math, and how fun is math? So in math, what we express this as is y equals to wx plus b. And this might look familiar, but let's break this down. So y is our output or prediction, which is lemonade sales, number of cups we sold. Lemonade sales, okay? And then the w right here is weight or the slope. Now, what is this? Let me talk a little bit about this. So this is how much sales increase per degree of temperature. So when the temperature increases from 20 to 21, by how much does my lemonade sale increase? It's very simple. And oftentimes it's the formula to find this is y2 minus y1 by x2 minus x1. You take any two data points in x and y and then deduce this. Now what is x? X is your input, or we also call it feature, and this right here is the temperature. And then we have this term b, which is bias or intercept. So basically that's sales when temperature is 0 degrees Celsius. So in our case, that's 0 right there. So we've broken down all the terms. I'm going to write that in a different color so that it's easier to remember. This represents our best fit line. And I'm going to just go over this once again quickly. So your W is the slope of line. It tells us how much the output changes when the input X increases by a unit. So if W equals to 2, it means that for every 1 Fahrenheit increase in temperature, you sell 2 more cups of lemonade. And then the B right here is your bias or your intercept. So this tells us what happens when X equals to 0. So whenever it's 0 degrees Celsius, how much lemonade do we sell? And then, and you know our X and Y's. So this should be clear by now. And let's walk through an example for linear regressions just so that everything's just crystal clear. So I'm gonna draw this for, what is this? This is our input or feature. I'm gonna have house size in square feet, okay? This is our X. and then I'm gonna have price in thousands. Okay, this is our y. So I'm gonna plot a few data here. So I'm gonna go with okay, let's do this. 500, 1,000, 1,500, 2,000. And then for price, I'm gonna go up to 300,000. So let's do, I'm just gonna keep it simple, 100,000, 200,000, and 300,000. Okay, so I have a house which is 1,000 square feet, and then the price for this house is 150. So what I'm gonna do is go to 1,000, which is here, and then I have to go all the way to 150, which is there. So if I do this, then this is where one of my data points exists. I have another house which is 1,200 square feet, so somewhere here, and then the price for it is 180, so somewhere here. So I'm gonna go like this, I'm gonna go like this, and of course this is very roughly done. And I have another house which is 1,500, and the price for this is 225, so somewhere here. Okay, and then bam. Okay, now finally I have my biggest house, which is 2,000 square feet, and then that one costs 300,000. So I have this. Now what we are going to do is we talked about our best fit line to the points, and I'm going to attempt to do my best to create a straight line here. Let me change the color. Okay, so this is my best fit line right here. Okay, so the equation for this, if I am not mistaken, should be y equals to 0.1x plus 10. Okay, so I have this equation now. So what I can use this equation, now that I have this amazing equation, is I can bring it here. And I have a friend who tells me that they are interested in selling their house, but they have no idea how to price it. But I have this amazing equation here with me. So they tell me, hey, I have a house. I have this house and it's 1,700 square feet. Okay, so they want me to find what the best predicted cost for this house would be. So what I'm going to do is give my predicted cost with a y hat, because it's predicted. So I'm going to do 0.15. For my x, I'm going to get the 1,700 square feet, and then I'm going to do 10. And then if my math is correct, that should be 265,000. So bam, now I have very easily given them how to price their house in order to be competitive in that market. And in real world scenario, of course, there can be a multitude of determining factors, and we're going to learn about all of that as we go, and we're going to learn how to deal with more than one input feature. But for now, we have done our first prediction with linear regression, which is amazing. Yay! So one question, how does the algorithm find the best fit line? Because I could have drawn this a number of different ways, right? Like, so I could have drawn this like this, or I could have drawn this like this. There could have been different ways for me to draw this. So how does the algorithm find the best fit line? So the computer needs to find best values for our W's and B so that the line is as close to the real data point as possible. So it does this by minimizing the total error, which is the difference between our predicted value and the actual value. So basically what we predicted the house would go for versus what it actually went for. So our predicted value versus, let's say it actually got sold for 245,000. So difference between two would be the total error, and would be the error, and then we would sum it all up to find the total error, and we're going to talk more about this in the next section. But the method used to do this is called gradient descent, and that's what I'm trying to gear you up for here. So let's recap some important concepts in linear regression before we move towards gradient descent. So linear regression, simple linear regression uses one input variable like we just did. And then multiple linear regression uses multiple input variables. For example, here it could have been house size, number of bedrooms, location, etc., which we're going to learn more about. And assumptions of linear regression is that the relationship between x and y is linear, a straight line fits well. The data has no extreme outliers that distorts the results. For example, a 2000 square feet house selling for all the way somewhere here, say for $1 billion, right? Then that sort of distorts the results. And then the variance of errors is constant across all data points. So basically there's no crazy fluctuations in terms of errors, and as we look at errors, this is going to come up again. So when is linear regression used? Predicting house prices based on size and location, or maybe forecasting sales revenue based on ad spending, estimating weight loss based on diet and exercise, determining exam scores based on hour studies, etc., etc. But when does linear regression fail? When the relationship is not linear. For example, predicting stock prices, which fluctuates very randomly. When there are too many features that are unrelated to the target. So it leads to what we call overfitting, and we're going to talk more about that as well. And when the data is too noisy, that is, random errors make the model unreliable. So linear regression is like drawing the best straight line through your data. It helps us make predictions using a simple equation. However, we must be careful to check whether a straight line relationship really exists before using it.